with that, I'll let Bret Bosma take it away.
All right, thanks for coming. So I'm going to talk a little bit about the testing of the autonomous wave energy converter, a little bit about the stuff we did in the WeSurf lab, and then mostly about what we did in the OH Hinsdale wave research lab. These results are, I just have got them, so they're pretty fresh, and this is like my first time going through it, so bear with me, please. So a little bit about the background of me and what I've been doing here in the last 4 years. So I'm a PhD student, this is my 4th year. So kind of when I started my research, the idea was that we would try to create a WEC design guide, so how to build a WEC. And so obviously that's a tough task because there's a ton of different WECs out there. So we kind of settled on a 2-body heaving point absorber, which Kelly Rule and I worked on a time domain model for. And then since then I've written a couple papers kind of outlining the frequency domain numerical modeling method using ANSYS Aqua, and then a time domain numerical modeling paper that I did using the results of the frequency domain to then implement a time domain in MATLAB Simulink. And so then the next logical step was, okay, we need to validate these models. And so Dr. Bret and I were looking for a way that we could get some hardware model validation. And so, here, this is from a document that EMEC, the European Marine Energy Center, put out that talks about different phases of testing of wave energy converters. And so it was real interesting. Yesterday, Terry Lettenmeyer, a PhD student in our group, presented on the testing of the Ocean Sentinel, and that was kind of a phase, I suppose that would have been like a phase 3, so in the open ocean. And so I guess I was going to show here that the testing that we did was kind of in this concept and performance, although we didn't quite run the number of tests that they recommend there. So at that time, it turns out that one of Dr. Vanjuan's students, Tim Lewis, was developing a scaled autonomous wave energy converter, and so I was able to get involved in that project. And so kind of the design goals that were kind of outlined for that was a target of 200 watts, full scale continuous power. There was kind of an emphasis on trying to make it relatively inexpensive, robust enough to at least survive the wave tank for the scaled prototype. And one of my goals for it, along with Tim's, was hopefully that it'll be a platform for future research. So we wanted to make, I guess what went into play there was we didn't want to destroy it at the end. We wanted to make it so that it could be used again if the need was there. So going through the design process, a lot of that was Tim's work, but we kind of settled on a 1/4 scale device, and we kind of modeled the environment after one of the NDBC buoys off of Galveston, Texas. So this is something I did where I took the NDBC data, so from 2005 to 2011, I took all the data and I basically looked at the significant wave height and the dominant wave period, and I just threw all the occurrences into bins, and then I came up with this chart of probability of occurrence. And so this is in percents here, and so you can see that most of the occurrences are between 3 and 8 seconds, and 0 to 2 meters, roughly. And so with constraints of the wave tank and the scale that we chose, we ended up pretty much testing the red box here. So from 3 to 6 second waves, full scale, and 0 to 2 seconds, significant wave height. So an important thing when you're building a scaled prototype is how you're actually going to scale things and how different parameters scale. So this is, we use the Freud scaling technique, and it uses this dimensionless number, the Freud number. For those MEs, you're probably a lot more familiar than I am with this, but basically the relationship is the velocity divided by the square root of the acceleration of gravity times the L term. And so that's proportional to the inertial force over the gravitational force, and you can kind of come up with these top scale factors from that. So the length in meters has a scale factor of lambda, which for our case, because we have a 1/4 scale, is an AWAC factor of 4. So that means if we had like a dimension that's 4 meters full scale, divide by 4 to get a 1 meter scale. So then, similar with the mass and the time. So the time is the square root of lambda, so our lambda 4 gives us a scale factor of 2 on the time. So then a real interesting one is the power. So power units can be expressed in mass times length squared divided by time cubed. And so when we analyze those units, we get a lambda to the power of 3.5. So when we look at power from the scale, if we look at a full scale power of 200 watts, we divide that by 128 to get just our 1/4 scale power. So we're looking at on the order of 1 to 2 watts when you scale it down to the tank testing that we did. So even though we have a scale of 1/4, the power is down in the 2-watt range. So through the design process, I modeled everything in SolidWorks down to every last nut and bolt, and that really helped with all the buoyancy calculations and just seeing how it was going to look in the tank and all the mooring configuration and everything. And then this is kind of one of the testing we did in the lengthened swimming pool. And kind of what it ended up looking like for the most part at the end. So there's these dimensions are in inches for the 1/4 scale. So 16 inches is the diameter of the float. Overall is about 120 inches tall. So then on the left is kind of the full scale dimensions. And then on the right is the scale dimensions in meters. So 1.6 meters would be the diameter of the full scale float, and 12 meters tall. So for our target of 200 watts, it's pretty large device, full scale. So for the scaled prototype, the power takeoff, we used a ball screw. And so you can see it here. The lead screw is about this long, and so this nut then travels up and down the lead screw and translates the linear motion into rotary motion. There's a gearbox, and then a DC generator, and then a coder on the top of that. And so this is a scaled prototype of a potential power takeoff, and so we're actually able to generate power and take it off the device. So this is just very basically how it was set up for most of the testing. So just a DC power supply. These are current sensors. We had a 4-quadrant drive, which is shown here, that we were able to control it with. and then that was attached to the generator. And then we had a variable load, which was just a pot. And then the current sensors and whatnot are in the box there. So the first testing that we did was on the linear test bed in the Wallace Energy Systems and Renewables facility. This was extremely valuable because it allowed us to check out the system and really operate it almost like it was going to be operated in the wave tank. And so it was really useful to get kind of a dry test first, so that we weren't like throwing it in the water and then needing to troubleshoot it, you know, in that environment. And so we did a system checkout, we validated the power output, we tried to characterize the overall efficiency of the device, and then estimate the losses in the device. So here's just a short clip of the running on the linear test bed. This is actually for an irregular wave input. So on the left you can see the ball screw. There's the nut that's attached to the float here. So you can see the power takeoff there. Any questions so far? All right, I'll continue. Okay, so all the results that I presented here, I've scaled them up to the full scale based on the Freud table that I showed towards the beginning, except for the resistance values, because it wasn't really meaningful to scale those up. So instead of having the 4-quadrant drive in there for this linear test bed results, attached the generator directly to a resistor, and essentially was looking at, so with these different resistance values, we ran the LTV in a constant velocity mode for these 3 different constant velocities, and so this is the full scale power output. So as we might expect, higher velocities give higher power output, and we kind of see a maximum power around the 7 ohm load there, which corresponds to the internal resistance of the generator pretty well. So then we did some efficiency calculations on those same runs, and so defined efficiency as the electrical power out of the system divided by the electrical power out of the system minus P, what we call P loss. So again, the P electrical is just the voltage times the current out of the generator. And then Pn we said was equal to the power associated with the kinetic energy in the system plus the power associated with the rotational energy in the system plus the P loss and P electrical. So the kinetic and rotational, if in fact it was at a constant velocity, these terms would go away, but I kept that in the calculations anyway. So as we can see here, not very good efficiencies throughout the system, but I can talk a little bit about where those inefficiencies ended up and what we might do to improve those in a bit. So then, so we were thinking, okay, we've got all these losses in the system. How are we going to incorporate those into our model if in fact we do want to incorporate those into the model? And so the easiest way would be to try to model those losses as just an additional damping term. And so we came up with this method of kind of saying, well, let's just get some ballpark idea of what the losses in terms of damping would be. And so we said that the F loss would be equal to the V loss times velocity, and then eventually came up with this V loss would be the power loss divided by velocity squared. And so we got at least kind of an order of magnitude of what the damping values would be, and so that helped informed our model before we did the testing. Those are higher than we would like them to be, but with what we had, that's what we ended up having. Okay, so now I'm going to talk about a little bit about the Hinsdale testing. So this is kind of just an outline of the large wave flume, the test facility that we used. So it's 104 meters long, 3.7 meters wide, and 4.6 meters deep. This is a side view here. So wave maker down at this end. We had a 1 and 12 each installed. The AWAC we put kind of in the central location here. So this is where the device was. These 3 lines here are where we put the self-calibrating wave gauges. So when I show results from water surface elevation, for my initial analysis, I just used the wave surface elevation at that particular wave gauge. This is the top view here. So you'll see in the pictures we have the phase space, the optical motion capture system set up around the device as well. Okay, so we had a lot of sensors. We collected a lot of data. These are kind of the highlights of some of the key things that we recorded during all the trials. So phase space is the optical motion capture system for those that aren't familiar with it. It uses active LED markers, and so for our particular test we had 8 wands. Each wand has 3 LEDs on it, which created 24 unique LEDs, and that allowed us to basically track the motion of each body in 3-dimensional space throughout the test. Like I mentioned, we had 3 resistance type self-calibrating wave gauges, and we also recorded a lot of data associated with the power takeoff, including the encoder signals, voltages, and currents. And then we had load cells on the mooring system. So I haven't analyzed that data yet, but it'll give us some sense of the mooring loads on the system. Okay, so these might be a little hard to see, but it's kind of the overall setup in the tank. And so this frame around the system here is the phase space frame. These are the cameras that are associated with phase space. This is the model in SolidWorks, which was really helpful. The installation of the mooring and the AWAC was really smooth, in part because it was all modeled beforehand. So here's the device in the water, and we can see these wands, these LED wands. So 4 wands on each body to track the motion. We had an umbilical here, so one of the lines is the encoder, the other line is the power from the generator. So the mooring system that we went with was a 3-point top mooring. So there was a pre-tension in each of the lines. The reason that we decided on this was mostly for ease, or it seemed like the thing that we could model the most accurately and simply put in the tank. It would keep it relatively where we wanted it to be, and so you can see the lines here in the water. 3-point mooring system. So a line across the back, and then I think you'll see in another. So this rear line comes back to a pulley over and then up, and then this is actually the load cell that is measuring the tension on the mooring line. So here's a little video of a couple of shots of the testing. So of course these are regular waves that we were running at it. setup. This is just at the beginning of a run, so the waves are just starting to come in now. Any questions so far as this is planned? Cool. So this kind of gives you a sense of underwater what's happening. This is kind of for a longer wave period, so you can see a bit of motion with more motion with the spar. Okay, so we actually ended up testing for 6 days. We ran 143 trials, so that's each set of waves we call a trial. We ran a combination of both regular waves and irregular waves. All the irregular waves were just a straight Pearson-Moskowitz, where we varied the significant wave height and the peak period. We recorded 23 channels of data at 50 hertz for every single run, and then all the phase space data for the 2 rigid bodies. So we ended up with quite a bit of data. So as I mentioned at the beginning, this was kind of a collaboration between myself and Tim Lewis. My kind of focus was on the model validation side. Tim Lewis was really interested in optimizing some control algorithms that he came up with. So I'm just going to talk a little bit about the modeling validation. So first of all, to kind of get our baseline operating point, we did a damping sweep. So we found the optimal damping setting for just kind of a nominal case, which I'll talk about in a second. Then using the regular wave data, calculated the response amplitude operators for each body. And so, as you'll see, I only used kind of one line in that 5x5 matrix, but we generated a 5x5 matrix of a sweep of regular wave height periods, regular waves. And then the other result I'll show is a power matrix for irregular waves. Again, we swept the significant wave height and peak period at a 5x5 matrix. And so this is kind of characterizing the power output over that range that I showed you from the Galveston test. Okay, so one of the first tests that we did was this damping sweep. So we put in a monochromatic wave input. These are 2 different test trials that we ran. So this lower one was an input of 1 meter wave height. Second one has 2 meter wave height. And essentially we just kept running a regular wave at it, and then at every 10 or so wave periods we would increase the damping applied. So of course, as I mentioned, this is full scale, but we basically kept increasing the damping all the way across here. And so as we see a nice peak in the about 1600 newton seconds per meter damping. And so then for the rest of the tests, for the characterization tests, we just set the damping at that value and let it run. So the way that we set the damping was through the 4-quadrant drive. So the 4-quadrant drive was in a current control mode, and so we took a velocity proportional damping term and created the torque control or current control that we then control the generator with. So here's the results from the response amplitude operator. And so again, this is for the regular wave input. And so kind of the way to interpret this, just say for this point right here, so I compared the measured wave tank data to the simulated Aqua data to the MATLAB Simulink simulated data. And so if we look at just this point right here, so we're looking at the float, and essentially if we put into the system a 1 meter amplitude wave, the result at this frequency, this period, the result then would be a 1 meter displacement of the float. And so basically at that, MATLAB Simulink said that this would be an exact wave follower at that frequency. What the tank test data showed was that it was closer to half of the amplitude for that. And so then we can go frequency by frequency and see what the results are. So we can see that, you know, at this point here, they matched up fairly well, but kind of diverged at those lower periods. And then we see the spar motion, and so we see a lot less motion of the spar as we would expect. So the RAO is much lower.
Bret?
Yeah.
And can you speculate as to the discrepancy in
I'm still working on that. I just got this result.
So these are wave periods, right? I mean, so in essence, it's frequency, right? I mean,
Yeah, yep.
Yeah, and then, so kind of that similar question, the Aqua and MATLAB Simulink predictions use your predicted damping values or the damping values from the testing on the linear generator, or on the linear test bed?
They used, so we applied a damping in Hinsdale that was constant, right? And so then I scaled that up, and that's what I used, just constant in the Aqua and the MATLAB Simulink.
Right, but so then the base damping that is just intrinsic to the generator, before you apply the damping, was that added in as well?
Yep.
Oh,
Yep.
okay.
Yeah.
Right, I have another question.
Yeah.
What is the natural frequency or period for these two bodies?
So around 4 seconds was the design.
Oh, what?
Full
no,
scale.
So shouldn't we start seeing a peak at 4 seconds then, if that's the natural frequency? And why don't you see that in the Aqua then?
So we see it in the power results, but we don't see it in the RAO results.
Really?
Yeah. So,
I mean, does that tell you then that the damping is so high that you're completely damping out the peak of that natural frequency?
that's very possible.
Yeah.
Yeah, it's very possible.
And is your input to the model here the measured wave height or the design wave height?
The measured wave height. So I took the results from the tank testing, and then I scaled that up as the input to the Aqua model.
Is the MATLAB model 6 degrees of freedom?
No.
Is it
Just
in
heave only. Yeah, heave only.
'Cause I noticed in the video it kind of, you might be losing some of that power to the pitch and the...
Certainly, yeah.
What is the difference between Aqua model and the MATLAB model?
So the Aqua, I ran Aqua not to get the results for the Aqua data. The MATLAB Simulink is based on the time domain simulator. So it starts with the Aqua frequency domain data, and then runs a time domain simulation just on the heave motion, which had roots with Kelly Brule when she was here. And that kind of.
And that's using the impulse response function from Aqua.
It uses the frequency domain data, which then you generate an impulse response function in the MATLAB code. Okay, so this is for the irregular wave runs. So again, the 5x5 matrix, because of limitations of the slope of Hinsdale, we couldn't actually run these two trials here. I apologize, you can't read these, but to show all the data at once here. So I just wanted to kind of show some of the actual output from the Hinsdale runs. So they're all on the same scales. And what we're looking at, this is time axis here, and then this is, again, scaled up, but power output. So,
May I ask, so
Yep.
what's the top run? I mean, what would that?
so, oh yeah, so this is, the columns are different period waves, or, sorry, peak period. So again, a Pearson-Moskowitz distribution, but different peak period. And then each row is a different significant wave height. So increasing significant wave height, increasing period.
Is it the same phase difference in the Pearson and the regular wave? Or did you generate a random phase?
So this is measured from Hinsdale,
Right.
and I'm not sure the method that they used to create the actual time series, but I can look that. I can ask Tim
I was
about that.
just curious.
So then if we kind of take this data and we look at the average value over the valid data ranges, this is kind of just a 3D plot of that same information. So again, the peak period, significant wave height, and then again scaled up average power. And so we see that kind of peak in the power data, around where it was designed. So it's interesting that it shows up there and not in RAL. So then take the same information and basically put it into two-dimensional tables. So these are the average power values here, and then significant wave height, peak period. So this is Fullscale, so with the small wave heights, very little power, and even at 1.7, we're at about 100 watts, where our target was 200 watts.
Are you on the very bottom?
So then, again, running the spectral wave. So what I did is I took the wave surface elevation from the Hinsdale trial, and then I scaled that both in frequency, or period, and in amplitude, and then that became my input to Aqua and to the MATLAB Simulink model. And so then that was run, and the same analysis from the previous two slides we've done, and this is the results from Aqua and MATLAB. And so then I did a percent error calculation. So this first one here shows the percent error between the Hinsdale and the Aqua simulation. So we can see that, in kind of this middle range here, we had relatively decent agreement. At the low periods and low wave heights, pretty significant error. And then this is between the Hinsdale Wave Lab and MATLAB, and then percent error between Aqua and MATLAB. So the Aqua and MATLAB, as far as power results, were relatively similar.
So is that scaling of power with wave height, what you expected? I mean, is it just that previous power dependence, or is it something more going on?
Sorry, can you repeat that?
Yeah, well, the power dependence, but you have increase in power with wave height, right?
Mm-hmm.
And does it increase like you expected it to? Is that just direct scaling of wave height to the free half?
May I comment on that? I've been following some of the work that Ted has been doing on this, and what happens is that you probably, are you familiar with the control algorithm that was used?
So for all of this, it was just
Also, it
velocity
was raw, no
proportional.
control algorithm at
Well,
all?
yeah, it was just a fixed damping.
Oh, okay, because usually what is under, you try to latch onto the phase of the wave, meaning that you get the maximal power transfer presumably when you get the peak. And
Yeah, there was
but
no
if there was
latching.
none, I mean,
There was no latching done on this.
okay.
It
No,
was
I
just,
mean the amplitude of the wave, not with respect to the phase of the wave. So the net power with 10-centimeter waves versus the net power with 5-centimeter waves. Going into it, you would have expected a certain scaling there, whether it was linear or nonlinear. Is that what you saw? How did the results show?
I haven't looked into that, so that's probably something I should look into. So you're saying related to the power in the input wave compared to the power out?
Well, the other thing is you're scaling up your output power from the scale model to full scale. And you said that the peak values weren't what you expected, but you're also scaling up your generator losses and everything.
Right.
Which won't scale the same as the power output.
Right.
So it'd be nice if there was a mechanical power measurement, torque and speed on the shaft going into the generator, but it wasn't available.
Right.
So the numbers in the boxes on this one are percent error between the models, right?
The bottom row.
The bottom ones.
This is the same as from the previous, so.
Okay.
So it's just, so the percent error between these two is
That.
here. The
Right.
percent error between these two is the center one and the center one. These two.
Okay.
It's-
So on the top plots, it's power is the
number
look at
and the
that.
shade.
Right, and if you do look at that, you are seeing an increase somewhat by the square of power as you move down the plot.
Right, so one thing that I kind of expected if we look at, instead of the wave height and the period, is that if you look at the equation for the input wave power, the longer the wave period, the more energy in the wave. But we actually saw more energy in the smaller periods. And so I think the explanation for that is that the slope was higher, and so we got higher velocities on the shorter period wave. So even though there was more power in the longer wave, we got a higher velocity in shorter period waves. Kind of the device, wave following and getting a higher velocity based on the smaller period.
I noticed that too on those.
I have one more question.
Yep.
Did you run an undamped case in the Hinsdale tank where you set the pot to 0 essentially?
So open or short circuit?
Free floating.
So open.
Yeah. Because I would expect if you were going to see a strong peak in the RAO, that would be where you would see probably the strongest signal for that.
I think one of the early runs we did, we unhooked the generator from
Okay.
anything and ran that. I haven't analyzed
Okay.
that data set though. Any other questions on this? Yep, so, in conclusion, successfully built and tested autonomous wave energy converter. It's kind of overwhelming the amount of data that we generated and how many places you could go with it. So any suggestions that anyone has for, so this is just kind of my first pass. I'm hoping to defend in July, so this is just kind of the first pass at it. And I think that we had relatively good correlation between the hardware and the numerical. There's some things that we need to try to describe, but it's a tough thing to do, and I think we did a relatively good job of that. So a friend of mine came and took some pictures of the testing, and I thought that one was kind of cool. questions? Dr. Pat?
Pretty low efficiency.
Yeah.
Where do you think, where's all the power going?
Yeah, so, well, I guess we could look at that. The bearing surface between the spar and the float is UHMW, is that the, yeah. And so there's certainly a fair amount of friction there, so there could be improvements in that, the surface between, so this is a PVC pipe, and then, so this is a 3.5 OD Schedule 80 PVC pipe, and then the UHMW is embedded in the float. And it, you know, it was fairly smooth, but there could be improvements there. If I had to do it all over again, probably the biggest source was, I think, in the bushings that we had. So the float rode up and down and, on these right here, and there's bushings right there. And if I had to do it all over again, I'd definitely put bearings there, which I don't think would be a great open ocean long-term solution, but for this couple-week test, I think would have helped there. There's a bit of inefficiency, certainly, in the lead screw and the gearbox and the generator. So
you're just using a simple motor for the generator.
yeah, DC generator.
Is there any plans to do some component testing on the test bed to isolate where the different losses are?
I don't have plans to do that, but
If you'd like to do it.
it's I don't know how you would kind of break that apart. I mean, it's
So you just have to, you know, take one component off at a time.
Yeah.
As, you know, try to do that, then that will help your scaling also, determining which
Put
would
it
scale
back
up
on
the
the
near.
linear test bed, take the motor, or take the generator off,
Mhm.
and then take the gearbox off, then the lead screw off.
And
well, so one of the problems with that is the way that we looked at the efficiency or the power out was the generator. That's what was our output power. So then how do you quantify the out, or, you know, the efficiency?
Force and load and cell.
Well, you can look at the different power input, I mean, from the linear test bed, as you take each component off. Since there's essentially no power output except for the frictional losses.
yeah, also it seems like you could characterize the generator itself and determine what power it will produce depending on how much torque you're applying to it.
So, yeah, so certainly could be done. One thing that the load cells on the LTB are extremely noisy, so those, you know, you can get reasonable data out of it, but it's pretty big error bars there when you are looking at those load cells, because, you know, even with this small device, the smallest load cells, at least that we have for the LTB, are on the order of 250 pounds, and so you know, you're almost getting down into the noise levels when you're looking at trying to get like efficiency out of the system. So almost a smaller test bed would be more appropriate for something like this.
How efficient is your generator? Any idea, mechanical to electrical?
I would have to look at the data sheet. You know, it's a combination of the generator, the gearbox, and the lead screw, and so those are broken out in the different data sheets, but I don't know off the top of my head.
Wouldn't efficiency also depend on how much the speed it's spinning and also the loading? So it's not just one number you can give it.
Right, but it kind of, in the data sheets they give kind of.
I've heard lead screw and ball screw, but from what I understand, they're two different things. Ball screws are.
Okay, that's totally me, just not the terminology. So it's ball screw, so that's the correct one.
Yeah, I
It's
thought the
lead
ball
screws.
screws were a lot more efficient than
Yeah, so we had 3 different options from this manufacturer, and the highest efficiency was with the Bosma, so that's what we went with.
So can you remind me again why, I thought the motivation was like to go smaller and cheaper? Is that why? Is that what you're trying to figure out? And so my question is like, how did you end up with this kind of whack? With all the different kind of whacks, why did you test this one?
Well, so certainly the biggest knowledge base at OSU, we thought was in, you know, a 2-body heaving point absorber. So being able to draw from that, you know, and looking at like Columbia Power or something, it's just 2 bodies, it's just one linear motion that you're trying to extract power from. So I guess that was how we kind of came to the point absorber. That decision was really made before I came onto the project, but and then, you know, on the full-scale device, you know, one reason we have the PTO outside here is because when we scaled it down, you know, we've got a 3.5-inch spar, and so to try to stick all that inside would have been certainly a challenge. So then we had talked about if we were going to build this full scale, probably try to embed whatever the power takeoff ended up being inside the device, instead of exterior as is there. I mean, part of our motivation was to get it up out of the water certainly, and you know, fitting that all inside was going to be quite a challenge.
Do you start to see an increase in incident wave power due to reflection for your longer trials?
I did not notice that in looking at the data. I know what you're talking about there.
Do you see a beating pattern in the wave gauges due to this reflected wave propagating method?
Like within a period you'd see a spike or something?
Yeah, I mean you would see, yeah, I mean you could see just a jump in the wave.
Well, with this spike, but it
No,
would be
it's
a
not.
long period of modulation in the wave. How long did you run these tests for?
So all the, actually both the regular and irregular, we ran 200 waves kind of nominally. So there was a ramp up time, then we ran for 200 waves.
And what kind of beach was in there?
I'm sorry?
What kind of beach did you have?
It was a 1-on-12. Yeah. Yeah. Oh, what kind? Yeah. Just the concrete slabs. Yeah.
So actually, for that question, Dave, what in your power output time series, was that from, you showed some power output time series, right?
Yeah.
And was that from regular wave conditions or from?
This is irregular. So,
What's the dead man in the middle of some of those?
So in the 4-quadrant drive, we kind of set a conservative current limit. And so on the LTV testing, we were fine, but on some of these spectral runs, especially in the higher power cases, we exceeded our current limit and it basically tripped our drive.
So you just manually reset it?
So then we manually reset linear trip.
So, not sure if you can do this, but could you take the power outputs and try to look at those spectrally to see if you see through time the development of a low frequency mode that would be equivalent to the beach reflection? Or, I mean, at some point you would expect that if the frequency of the wave is long enough, it wouldn't show up in your power matrix. Or in your, okay, never mind, I'm just talking to myself at this point.
I mean, I think you could see it in the time series data
Yeah.
more easily than that, but I haven't really zoomed in on that. So in presenting this, can you give me some feedback of what would be most useful to show with zooming in on one of these, you know, up close, would showing the regular wave power results be more appropriate?
Maybe like headers on the top?
Yeah.
But as far as,
Would a time series of the wave surface elevation be useful to see?
I couldn't see it up close.
Up close,
Maybe
so
like
just a small section there.
30-second band.
Yeah, like 4 or 5 wave periods or something.
Well, if you wanna look for the reflection, I mean, the easiest place to look for is in the wave, water surface elevation time series. And that tank will oscillate at about 50 seconds if you get a lot of reflections in there.
Okay.
So you wanna look at time series that are longer than that, to
Right.
see the beating, but.
Okay. So another thing I did, which I didn't put the results here, was, you know, we asked Hinsdale to provide this wave for us. So then I took a look at what I measured on the wave gauge and said, well, what did we get compared to what we asked for? And so for the regular waves, the period was right on. Like, it was just like pretty right on to what we had asked for. The wave height was slightly lower for each case, and it varied with the different heights. And so that's why I used that results data as my input to the other models. For the spectral cases, they were off by quite a bit, both in period and in height. Quite a bit lower significant wave height than was requested, and the periods were off as well.
Great presentation.
Yeah.
Yeah.